Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be taking a look at the proportional odds model that we were discussing in the last lecture, and we're going to be fitting this using R. Right, so in the last lecture what we saw was that the likelihood that comes out of discrete time survival data sort of looks like a binomial likelihood, or it exactly looks like one because it is, which sort of gives us this idea that we could use logistic regression, or GLMs, in order to fit a model for the hazard function in discrete time data, right? And doing so, we saw how we can use the time variables as an indicator and just fit sort of a standard constant hazard function, or we can start adding in covariates into our GLM. And in particular, there's this really nice natural parameterization wherein we include the covariates that don't interact with time, and doing so gives us this proportional odds model, okay? And so in today's lecture, what we're going to do is we're going to load in some data and then sort of fit these models. And all of these model fitting techniques you've seen before because it's all using GLM, but we'll go through it in some detail. As always, the data that I am working with are posted on the course website, and my code should be up there as well. If you have any questions, please let me know. But otherwise, I will open up R and we can get started. So the first thing that I'm going to do is just read in the data. I'm going to call this AML. It's a data set from a leukemia trial. And so if I just take a quick look at what this looks like here, just take a look at the head. You can see that we have these IDs, the time variable, and the status variable, as well as this X, which is indicated as either maintained or, and if we look at, say, what the unique values of AML X are, you can see there's maintained and non-maintained in this data set. So the ID obviously represents the individual, the time is for the time that the event occurs, and then the status indicator is such that a 1 represents a censored individual and a 0 represents someone who had the event occur. Okay, and so the main question of interest is about this X variable here. And the basic idea is that there are two different types of therapy for the leukemia that's being tested here. So it's either maintenance therapy or non-maintenance therapy. And the question of interest is doing the maintenance therapy beneficial for the survival time of the individuals? All right. So the first thing that I actually want to do with this data is transform it from this person level data to person period data, right? And so we had seen that in this previous the previous lecture that we were looking at with the R code, where we saw that there's sort of the two different formats, kind of similar to what we saw with long and wide data, but in this case, obviously we have person period versus person level, and so this function here should be available on the course website, this PLPP, and we've seen this used once before, but what I can do is I can come down and I can define, say, AMLPP, which will be the person level person period. We call it on the AML, the ID is ID, the time is time, the status, or the event is status, and then the direction that we want to go to is period. Right? And so if I run that and I can take a look, say, at the person period format now you can see that, for instance, with individual number 2 here, there are 2 rows for this individual because they had an event in time 2, right? So we have this with their first row and then for the second row. And I guess they were actually censored in this case, right? So that's our data that we're sort of going to be working with here. Now, with the logistic regression model for survival data, it's as simple as actually just fitting a logistic regression to the data that we have here in this person period format. So we can start with, say, the base model, and we'll just call this model logistic regression here. And it's just going to be the GLM. The outcome is our status variable. We want to have it as a factor, so we'll say as factor time, and then we use a -1 to indicate that we don't want an intercept. Remember that that intercept would sort of over parameterize the model. The data set is just going to be this AML PP data frame here, and the family is going to be binomial. And if we run that, you can see that we get a model fit. And of course, we could start investigating this in the same way that we are used to investigating logistic regression models, right? So I can do a summary here, and we can see that there are these 6 different coefficients estimated, and each of these would correspond to a different time period, right? So this is for the first, second, third, fourth, fifth, and sixth. And within each of those, what we saw was that if you want to convert these back to a probability, then those are estimates for the hazard function in that time interval, right? And so the way we typically convert within a GLM is we want to use the xbit function, right? And maybe I'll just quickly define the xbit function here. And this is going to be 1 over 1 plus the exponential of negative the argument here, right? So now what we can do is if we want to get a hazards estimate, so hazards from the likelihood ratio, or not the likelihood ratio, the logistic regression, then we can call the xbit on the coef of the model logistic regression. And if we just take a look here, hazards with the likelihood ratio, you can see that we get sort of a different hazard estimated in each time period here, okay? Now, previously, before we had used the logistic regression to do this, we had estimated a hazard non-parametrically in each of the time periods. And the way that we had done that was using the prop table, right? And so if we had taken the table from that corresponds to the time and then the status here, right? This gives us a table that sort of summarizes how many individuals had each. And so then we can do the prop table of this. I believe we have to provide the argument 1. And that's going to give us these estimates here, right? And so if I do, say, a C-bind of this along with and let's just round the hazards that we just estimated here. And the reason we're doing this is just to make sure that the decimal precision isn't too much. But if we tack on this column of the estimated with the logistic regression, you can see that the hazards that we estimated are exactly the same, right? And so what's this telling us? Well, it's telling us that because we were using that likelihood ratio or that likelihood formulation for it, when we fit the logistic regression here, we can actually see the idea being that the hazard function that we were using, the estimate for the hazard function that we were using, is actually the exact same as the maximum likelihood estimator. And we saw this within the transition models as well, so it shouldn't necessarily be a surprise. But when we're not including any different covariates in here, we just estimate the same hazards, right? But the benefit becomes, first, now that we're using a GLM, we can start testing the model in the ways that we sort of know how to. And second, we can include those additional covariates that we might be interested in, okay? And so the idea here, let's take a look at the summary of our model and just sort of try to assess the significance here, right? Looking through, right, we can see that most or some of these do appear to be quite significant and some of them appear to not be significant. But if I'm taking a look at our standard errors, right, you can see that for periods 2, 3, and 5, the standard errors are somewhat reasonable. But for the rest of the periods, we actually see that we have these really high standard error estimates, right? 17,730 as the standard error estimate for this, almost 6,000, almost 4,000. And so the big problem with these data that we're looking at here is if I just do, say, a num row on the data set, you can see that there's only 23 observations. And so we really do not have enough data to be fitting the models that we're trying to fit right now, right? At least not to be able to test them with nice hypothesis testing. And so in the real world, if I were trying to fit this, probably what I would do is start trying to collapse some of these categories or, approach this in a less hypothesis-driven manner, right? Just try to get some idea of what the trends are without doing this. And so there's this caveat that I want to put on to everything that we're doing here, which is we're going to walk through how to do all of the hypothesis testing, how to do all of the variance estimation, the intervals, etc. And that's to show you how to do this. But if you were to get your hands on this data set in the real world, I would be very cautious about doing this. And that's only because you're not going to be able to get sort of meaningful results when you're looking at standard errors that are, thousands of times larger, 1,000 times larger than your estimate, right? It's just not going to be super useful for you. Now, everything that we do is still valid. It's just there's going to be a lot more noise in the data than these methods can reasonably handle. Okay, but if we wanted to, say, make some confidence intervals around our hazards, we can do that because we're using this nice logistic regression formulation. And so we could get the variance of the hazard, which you can get with the VCO function here, and just pass in the logistic regression model. And then we could get the standard errors from this, which is going to be the square root of the diagonal of that variance matrix that we just had, right? And so if we take a look at those standard errors, they're going to be the same standard errors we saw in the coefficients table we were just looking at, right? But now if we wanted to, say, do a confidence interval around the estimated hazards, we could, and maybe I'll output this in a sort of tabular format here. If we do the xbit of the coef for model logistic regression, and we subtract off the Q norm times by the standard errors, then maybe we will just include the coef in the middle here, and then, and I forgot to put this in the xbit, and then we can include the upper bound on these intervals, right? And so part of the nice reason for formulating the problem in the way that we have is that all of these standard confidence intervals, all the standard inference that we're used to doing, we can still do here, right? So you should be very used to building out confidence intervals in this way. And you can see, maybe I'll round this whole thing to just 4 decimal spots just to give us a little bit easier time of looking at it. But you can see that we have, confidence intervals that range from 0 to 1. This is a probability, so that's not a very useful confidence interval, but for time period 2, we have something that's kind of interesting, right? We have a lower bound and an upper bound, and same thing with 3. 4 and 6, not so much, but with 5, we also have something. It's quite a wide range, but, we can sort of look at it that way. And again, all of this inference should be quite natural to you based on everything that you've seen with logistic regression and GLMs, more generally speaking. Okay, so that's the hazards directly without the use of any sort of variates. We could also get the survival function estimates, right? So if we want to look at the survival function, well, we can get the estimate here through that relationship with the hazard functions, which is the cumulative product of 1 minus the hazard function, right? And so we can do the cumulative product of 1 minus our hazards from our logistic regression here. And if we take a look at these here, you can see that we have these different survival probabilities. They start at 1 and then they decrease from there. Okay, and so in the lecture where we were talking about the different sort of conceptual understanding of this, we had talked about a way to generate confidence intervals for the survival function. And what that required was this G matrix, and the G matrix sort of takes a lower triangular form where the hazards are kept inside of rows, okay? And so there's a handful of ways that we can do this, but if we call replicate here, then basically what replicate is going to do is it's going to repeat the argument that we pass it a certain number of times. And so the number of times that we want to repeat this is the length of our hazards function here. And what we want to repeat is the negative of our hazards function, right? Because that's sort of the general form for this G matrix here. So if I do this, you can see that what we're going to be having here, and maybe again, I will just round this just to output this a little bit more nicely into our console here. You can see that we have these 6 different columns here. Each one of them has the hazard for the different time period, right? So we've repeated it 6 times. Now, the G function or the G matrix actually has them in columns rather than inside of their rows. And so I want to come in here and I want to take the transpose of that, so just wrap T around this. And you can see now we have these 6 different columns, each of them representing the hazard, right? And so this is sort of the base of our G function here. So I'll just define that to be G. Now, the difference between this and what G actually is that G should just be the lower triangular half of this matrix, right? And so what we can actually do is if you call upper triangular as a function, and you give it a matrix here, so say G, what we're going to see is that this produces a true and false, where the trues represent all of the indices that would be in the upper triangular matrix, and the falses go everywhere else. And so what I can do is I can come in here and I can select from G the upper triangular. So this is going to select out all of the indices that have trues, and I can just put a 0 into those, right? And so if I take a look at what G is now, it's a little bit hard to see, but maybe again we go round G to 3. Does that output it? Can unname it maybe? There we go. That's a little bit easier to see here. You can see that we have this upper triangular matrix where in the first column here, we have our hazard at 1, hazard at 2, hazard at 3, and so on. And then the upper triangular portion is all zeros. Okay, so that's sort of what we're doing. But now we can use this G matrix and we can use the estimated variance matrix from the hazard function in order to compute a confidence interval for the log transform of the survivor function. So maybe I'll call this log survivor function variance. And we saw that that's going to be G multiplied by the variance, the estimated variance of the hazard, times by the transpose of G. Okay, and then we can take the log S standard error is going to be the square root of the diagonal of that matrix. And we can also get our log survivor function here, right? Don't want to forget that piece. And so we had called that survivor logistic regression there. Okay, and so now if we wanted to have a confidence interval around the survivor function, what we're going to do is we're going to build the confidence interval based on the log S and the log S standard error, and then exponentiate that, right? And so I can come up here and essentially just steal this code, put it down here, but instead of doing the X bit, we want to do the exp, right? And instead of the coef of the model here, we're going to be looking at the log survivor function. Just replace that. And instead of the hazards standard error, we want the log survivor standard error. And if we run that, you can see that we get these estimates here, right? And so again, these aren't necessarily the most useful estimates, as you can see there, right? But this process will, generally speaking, work for generating out the confidence intervals for our survivor function. Okay. Again, a lot of this is just owing to the fact that this hazard variance is quite a large matrix, right? And so you end up in a situation where you might not sort of be perfectly valid. All right. So where can we go from here? Well, we saw that after using the basic model, we could also do some level of adding in covariates for the proportional odds assumption. Okay, and so the idea there is that we can take the exact same model that we have and just start adding in covariates, and by doing so, we can fit sort of new models, right? So I can do a sort of proportional odds model here, and as I was saying at the outset, the main question of interest for us is whether this X factor that we have, which is whether they're on maintenance therapy or non-maintenance therapy, whether that is significant. And so if I do the same model here as factor time, subtract off 1 because of we don't want an intercept, and if I just add in as factor X, pass in the same data, pass in family as binomial, now what we've done is we've fit this proportional odds model, right? And so in our proportional odds model here, you can see that we have the same time estimates here, but we also have a coefficient based on the whether or not it's a non-maintained therapy. Okay, and if we just take a quick peek at the p-value, we can see that that doesn't actually appear to be significant, at least not in this data. And so that sort of allows us to test this hypothesis as to whether beta 1 equals 0, right? And we can see that we would reject or fail to reject. And so because we failed to reject, we're saying maybe there's not actually really an effect there. All right. Now, we could also do all of the same types of confidence interval procedures here, right? And you've seen confidence intervals for model coefficients very frequently, right? So you would be wanting to go the estimated value here, say negative 9,557 plus or minus 1.2147 times by the z-score that we care about, right? And that would build out a confidence interval for beta 1 if we wanted to do that. All right, and so you could do that. You could test whatever other hypotheses, but looking at the fact that this isn't particularly significant anyways, it might be worth sort of not doing that. Okay, so the last thing that I sort of want to show is this testing of the proportional odds assumption, right? Because by including it in this way, we are making that strict assumption that the hazard at each time point is going to be proportional based on the different levels of this factor. So the hazard at time 1 is going to be multiplied by the same thing as the hazard at time 2 if you're in x equals 1 versus x equals 0, right? And so we had said that we could actually test whether that's a valid assumption by using a saturated model and then deviance testing, right? So if I do a model saturated here, I can fit GLM and the status. And what I want to do is I want to take the as factor time intersecting with as factor x, still subtract off the intercept. The data is going to be the same thing. Family is going to be the same thing. And if I fit this model now, it should be status, not stats. Then you can see that we have this sort of fully saturated model, or at least fully saturated from our perspective here. And what we can do is we can just deviance test this versus the underlying model that we care about, right? And so we could do just an ANOVA here, model saturated, and the test that we would be running is a chi-square test, right? And so if I run this, you can see that the p-value is going to be quite high, right? We do not reject the null. Now, if you don't remember your deviance testing from GLM, we can do this sort of another way. We can say that the D0 here is going to be the model, the proportional odds model, and we can grab the deviance there. And we can say that the D1 is going to be the model saturated. You can get the deviance there, deviance. And then we care about the delta, which is D0 minus D1. Right, so we can fit all of these, and we can see that the delta of the deviance is this 1.83327. That's where this is coming from. It's 1.833 in the ANOVA, right? The number of degrees of freedom that we would want to test against is the model, the degrees of freedom from the residual in our reduced model. Subtract off the model saturated degrees of freedom from the residual, right? And so we can see that there's 4 restricted parameters there. That should make sense. And then we can get our p-value doing 1 minus p chi-square. And the test statistic is delta D. And then you can see that we get this 0.776, which is, or 0.766, sorry, the same thing down there. So we would fail to reject, and we can use the proportional odds assumption. Okay. And so sort of the nice part about framing it in this way, right? We ran through it a little bit quick. This probably wasn't the best data set to use, but I think it's also helpful to get your hands on real world data and see sort of some of the ways that the theory falls down, because in the real world, our data is far too noisy to sort of make use of all of the strong theory that we have. But the reason that this is so nice is because this whole process has essentially been transform our data into this usable format, and then we can just fit GLMs. And as soon as we start fitting GLMs, our confidence intervals are going to be exactly what we would expect. And the only thing that we have to do a little bit of working around is getting out this survival functions variance estimates, right? So to get the confidence intervals here, we have to make sure that we're sort of doing that correctly. But other than that, everything sort of works out really nicely for us, right? And then we can use our proportional odds assumption here just by including other factors. If it's not valid, we can test that it's not valid, and we could use a sort of a more complex model. But this proportional odds model simplifies really nicely in the interpretation of what the coefficients are, right? And so sort of to, I guess, formalize what this is, we would say that if I take a look at the coef from the proportional odds model here, this negative 0.9557, right, if we take the exponential of that, this 0.384 is going to be the multiplicative value for those who are in the non-maintained versus in the maintenance therapy in terms of their hazard, right? So you would take the hazard of the person in the maintenance therapy, multiply it by this value, and that would be the hazard of the person in the non-maintenance therapy. But as we determined, this was not a significantly different value from 0, right? And maybe it actually is in practice, but we didn't have enough data to sort of conclude that. So I hope all of this makes sense. I will have posted this code with thorough commenting as well as the data online. And I would also encourage you to take a look at some of the other data sets up there and try to work through the same process with those data sets. There's a lot of data online that's going to have larger sample sizes that some of this is going to work out a little bit nicer for, but nevertheless, hopefully all of this makes sense, and I will see you all in the next lecture.